Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC403. Topics: continuity equation, inconsistency of Ampere's law, Faraday's law, and Maxwell's equations for time varying fields. Lecture level outcome. After completion of this class, the student will be able to apply the knowledge of time varying fields to develop Maxwell's equations. So far we discussed about electrostatics, magnetostatics, and from now onwards our discussion is with time varying fields. Static electric field is due to stationary charges, and static magnetic field is due to steady current, and time varying field is due to time varying current. Time varying field is also called electromagnetic field or waves or electromagnetic waves. The time varying field must satisfy continuity equation. It is the base for time varying field. Continuity equation is the base for time varying field. Continuity equation. From the principle of charge conservation, the time rate of decrease of charge within a given volume must be equal to the net outward current flow through the surface of the volume. Thus, current I out coming out of the closed surface is here. From the principle of charge conservation, the time rate of d by dt, decrease of negative sign, the time rate of decrease of charge within a volume. Volume means it is a closed surface, must be equal to the net outward current flow through the surface of the volume, that is I out, closed surface integral of j dot ds. It is given by equation 5.40. Here Q in is the total charge enclosed by the surface. By applying divergence theorem, this term will become volume integral of del dot z dv, equation 5.41. Once again, I am rewriting equation 5.41, and the RHS of continuity equation minus d by dt of q in is equal to minus d by dt of q can be written as the volume integral of rho v dv. And if we move d by dt into the integration, it will become dou by dou t, and now it will become minus integral of dou rho v by dou t, integration with respect to volume. Let it be equation 5.42. Now here, if you observe the RHS volume integral of del dot z dv and minus volume integral of dou rho v by dou t from 5.41 and 5.42, it will become this equation. Here both are volume integrals. You can separate the term del dot z and minus dou rho v by dou t, that is del dot j is equal to minus dou rho v by dou t, and it is called continuity equation. where the value of J is equal to sigma into E electric field, and it is called point form of Ohm's law. Inconsistence of Ampere's law. Uh, just now we discussed about continuity equation. Time varying field must satisfy continuity equation, and the continuity equation is given by del dot Z is equal to minus dou rho v by dou t. And for static fields, we recall that from Ampere's law, del cross H is equal to J. Here H is a vector. The del dot of del cross of any vector is equal to 0. That is del dot J is equal to 0, and this is valid only for static fields, not for time varying fields. Here del dot J is equal to 0, and this is valid for static fields, and for time varying fields del dot J should not be equal to 0. This is the main requirement of time varying fields. Means that this particular equation del cross H is equal to J is insufficient to validate it for time varying fields. To validate Ampere's circuit law for time varying fields, some extra term is to be added. Let it be ZD. The extra term to be added to the Ampere's circuit law to validate this equation for time varying fields. Here, the extra added term is represented with equation 9.20. Once again, applying divergence on both sides of 9.20. Here H is a vector del dot of del cross H. Divergence of curl of any vector is equal to 0, and del dot Z plus del dot ZD. Now here you can substitute minus dou rho V by dou T and plus followed by del dot ZD. After simplifications, what you are going to get is the value of ZD as dou D by dou T, where D is the electric flux density. Now, the Ampere circuit law for time varying fields. This will become del cross H is equal to J plus dou D by dou T, and this is valid for time varying field. And it is one of the Maxwell's equations for time varying fields. Faraday's law. Here, consider a closed loop with some battery and a resistor in the circuit. According to Faraday's law, he discovered that the induced EMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. And this can be mathematically expressed as the VEMF is equal to minus N into dou psi by dou T or d psi by dt. Time rate of change of magnetic flux linkage by the circuit. It will give the value of induced EMF. Once again, I will rewrite VEMF is equal to minus N d psi by dt. Here, this psi is the magnetic flux linkage by the circuit. And if the value of N is equal to 1, the previous equation will become VEM is equal to minus d by dt of psi, that is given by equation 9.4. And in terms of E and B, 9.4 can be written as VEMF is equal to closed line integral of E dot dl. It is equal to minus d by dt of open surface integral of B dot ds. Here it is the time varying electric field. Here this term are written from the previous equation, minus d by dt of the magnetic flux is simply the open surface integral of BDS. And if it is closed surface integral, then from Gauss law for magnetic fields, an isolated magnetic charge does not exist, so it is equal to 0. Please make a note, the integration is a open surface integral, not closed surface integral. Here it is open surface integral. Now apply Stokes theorem. Here Stokes theorem, closed line integral of A dot dl. It gives a relation between single and double integral del cross A dot ds. Now it will become surface integral of del cross E dot ds minus dou by dou t B dot ds. Here both are surface integrals. You can equate it as del cross E is equal to minus dou B by dou t. It is given by equation 9.7. Once again, I will read the final equation obtained from Faraday's law. Del cross E is equal to minus dou B by dou t. Here what it means is del cross E is equal to minus mu dou H by dou t. Here the physical significance of this equation is, in an electromagnetic wave, both the electric field and the magnetic fields are present at a time. They are interlinked, and always in an electromagnetic wave, electric fields and magnetic fields are perpendicular to each other. Here del cross E is equal to minus dou P by dou T. It is one of the Maxwell's equations for time varying fields. Now Maxwell's equations for time varying fields, for that you can follow the notation D, B, E and H. This is the order to write the Maxwell's equations. Del dot D equal to rho V. Del dot B 0. Del cross E minus dou B by dou T. Del cross H J plus dou D by dou T. Here once again, please make a note. These are the Maxwell's equations for time varying fields, or in simple words, these are Maxwell's equations in integral form and their associated laws derived from Gauss law, non-existence of isolated magnetic charge, Faraday's law and Ampere's circuit law, inconsistence of Ampere's circuit law. To validate Ampere's circuit law for time varying fields, we followed continuity equation to derive this equation. Sample problem. Here, the magnetic field intensity is given in free space. You're supposed to determine the value of current density J if the fields are time invariant. If it is time varying field, then what is the value of del cross H? J plus dou d by dou t. What type of field it is? It is time invariant, means dou by dou t. The variation of the term with respect to time is 0, and this can be termed as 0. It will become del cross h is equal to 0. Simply by calculating the curl of magnetic field intensity, you can determine the value of conduction current density J. Units are ampere per meter square. Once refer to the other biography, Michael Faraday and James Clerk Maxwell. Here, Michael Faraday is the greatest experimentalist who ever lived. Some more information about James Clerk Maxwell. He is regarded as the founder of electromagnetic theory. Once refer to his biography. Thank you. We will meet with the next lecture.